Hi Year 11 and welcome to our second lesson on combinatorics. In this lesson we're going to look at the pigeonhole principle. So far we've learnt about the fundamental theorem of counting and factorial notation. So last lesson I left you with this question. The letters A, B, C, D and E are each written on a card and then the cards are dealt in a random order. How many different orders are there? 5 factorial or 120. Calculate the probability that the vowels are together. Now the vowels, of course, are A and E. And the way to tackle this sort of question, I just draw up 5 different places and we count the places that we can put the A and the E. So they could go here, here, or here, or here. So there's 4 positions that the vowels could go in. But then I noticed that they don't have to be in this order, A and E. They could be in the order E and A. So I'm going to double that. Now once I have placed them in one of those positions, there is 1, 2, 3 factorial ways that I can place the other letters. So altogether there are 48 different arrangements. And the question is, what's the probability that the vowels are together? Well, that will be 48 out of 120. Okay, so let's move on. Here is the pigeonhole principle. If n plus 1 pigeons are placed into n pigeonholes, then at least one pigeonhole must contain 2 or more pigeons. Here's an example. A school class contains 27 students. Explain why there must be at least 2 students whose names start with the same letter. Okay, do you have any idea why that might be? It's because there's 26 letters in the alphabet. Now, I often tackle these sorts of questions talking about a worst case scenario. In this case, the worst case scenario is the first 26 students that I encounter, their names all begin with a different letter. But then there's a 27th student, and that's going to cause a duplicate. Do you understand? So by the pigeonhole principle, if there are 27 students, then at least 2 students' names begin with the same letter. Is a past HSC question. Each of the students in an athletics team has randomly allocated their own locker from a row of 100 lockers. What is the smallest number of students in the team that guarantees that 2 students are allocated consecutive lockers? So we'll start to draw this up, but of course I'm not going to do 100 lockers. I'll just do the first 5 and say the last 2. And let's think about how many students we can place so that none of them are next to one another. So we'll put a student here and one here and one here, and there will be one in the 99th locker. And that's 50 students. And the 51st student is going to cause 2 or more students to be allocated consecutive lockers. So our answer is D. Now, pigeonhole principle questions take many different forms, and here's a geometric example. Prove that among 5 points in an equilateral triangle of side length 2 centimeters, there must be at least 2 points which are at most 1 centimeter apart. Now I can tell from these words, at least, at most, that it's probably pigeonhole principle, but where are the pigeons and where are the pigeonholes? Well, this 5 points here, they're the pigeons, and there's a bit of a trick to finding the pigeonholes. The equilateral triangle has side length 2 centimeters, so I can construct 4 equilateral triangles inside it. And pause the video and have a go and see whether you can finish this question off. All right, so worst case scenario, we're going to put 1 point in each one of these spaces, and then by the pigeonhole principle, a 5th point must go in the same place that there already exists a point. So there must be at least one triangle containing at least 2 points. Now, these triangles are 1 centimeter around the edges. So the maximum distance any of those 2 points can be is 1 centimeter. So therefore, by the pigeonhole principle, there must be at least 2 points which are at most 1 centimeter apart. Here's a harder question. Suppose we have 27 distinct odd positive integers, all less than 100. Show that there is a pair of numbers whose sum is 102. Now this one doesn't even look like pigeonhole principle because we don't have the words at least anywhere. However, they are implied in this second sentence. We could have written this as show that there is at least one pair of numbers whose sum is 102. Now again, like the last example, we can see the pigeons. Okay, there's 27 of them, but there are no pigeonholes. And the way to get them is to pair up the numbers so that most of them add to 102. So we've got 3 and 99, 5 and 97, 7 and 95, all the way up to 49 and 53. And there are two odd numbers left over. They are 1 and 51. We can't pair that up to make 102 because we'd need 101. And we can't pair the 51 up because we would need another 51. So they're going to be by themselves. Now here's the pigeonholes. There's 24 pairs that add to 102, plus this one, plus this one. All right, worst case scenario. Suppose we have one of each of these numbers in our 27 distinct odd positive integers. Say we've got the 3 and the 5 and the 95 and one in each of these ones, dot, 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 and the 49, and we've got the 1 and we've got the 51. Then we have 24 pairs plus 2, these guys here, which is going to make 26. But we've got 27 distinct odd positive integers. So once we've filled up each of those pigeonholes, we're going to get one of the other numbers, which is going to make a sum of 102. So 26 pigeonholes altogether. By the pigeonhole principle, at least one of these holes must contain two numbers. Therefore, there must be at least one pair of numbers whose sum is 102. Now we've been talking about n plus 1 pigeons being placed in n pigeonholes, but we can generalize this principle as follows. If n pigeons are placed into k pigeonholes, and n is bigger than k, then at least one pigeonhole must contain at least n divided by k pigeons. So let's just put some numbers to this. Suppose we've got 25 pigeons and 4 pigeonholes. Then at least one pigeonhole must contain at least 25 divided by 4, which is 6.25 pigeons. Okay, let's see how we use this. The 253 students in a school are divided into 4 houses. At least one of the houses must have at least x students. Find the value of x. So in this case, n is 253 and k is 4. When we do our division, we get 63.25, which is approximately equal to 64. Now, we always round up. Let's have a think about why. Suppose we take our 253 students and we divide them evenly across the 4 houses so that there's 63 in each house. There's going to be one student left over, and that student is going to have to go into one of the houses. So we're going to round up to 64. Thus, at least one of the houses must have at least 64 students. Here's a past HSC question. The members of a club voted for a new president. There were 15 candidates for the position of president and 3,543 members voted. Each member voted for one candidate only. One candidate received more votes than anyone else and so became the new president. What is the smallest number of votes the new president could have received? So we've got 3,543 pigeons, 15 pigeonholes. Looks straightforward, doesn't it? 236.2, so at least one of the candidates has to receive at least 237 votes. But B is not the answer, and this would have tricked a lot of students. Part of the problem is this notation here, because when we use remainder notation, we notice that it's 236 remainder 3. There are 3 votes left over. It's easy to work that out. It's just 0.2 times 15. Now, suppose we take our 3,543 votes and we distribute them evenly amongst the 15 candidates. I won't draw them all up. And we've got 236 here and 236 here and 236. And we go all the way to 36. And we've got these 3 votes remaining. If I distribute those to 3 different candidates, I have 3 people on the same number of votes, but one candidate received more votes than anyone else. So what I've got to do is take one of these and allocate it to the new president, and then we will get a new president. So the smallest number of votes the new president could have received is 238, which is C. Now the most important part of these questions is to figure out what represents the pigeonholes and what represents the pigeons. And we've seen a couple of times in this lesson that it's not always obvious. All right, I'm going to finish off with a harder question, but I'm not going to tell you the answer until the next lesson. In a group of 6 people, each pair are either mutual friends or mutual enemies. Show that the group contains either 3 mutual friends or 3 mutual enemies. Good luck. And our next lesson is on permutations.